Metal injection molding, commonly referred to as MIM, combines the unique metallurgical capabilities of working with metal powders and the shape-making advantages of injection molding. The process begins with the use of very fine powders, generally below 20 microns and often smaller than 10 microns. These powders, which are preferred to be highly spherical because of the flowability characteristics required in the molding process, are generally produced by atomization, mostly using high-pressure gas or water, although other production methods are also employed, depending on the metal involved and the specific microstructures and properties desired. An extremely wide variety of metal alloy compositions are possible with MIM. In fact, dozens of different compositions have been produced by MIM fabricators. The most common alloy families are iron, low alloy steels, and stainless steels, and materials may be available as master alloys or as pre-alloys. But metal powder by itself cannot be used in the injection molding process. Rather, it must be formulated into a feedstock that, when heated in a molding machine, achieves a viscosity that enables it to be forced under pressure into the mold. This feedstock is made by combining the metal powder with a thermoplastic polymer, known as the binder, in a hot state in order to create a mixture in which every metal particle is uniformly coated with the binder. Typically, binders comprise 40% by volume of the feedstock. Once it is cooled, this mixture is granulated into pellets to form the feedstock for the injection molding process. On the molding machine, the feedstock pellets are loaded into a hopper from which they are gravity-fed into the machine's barrel, where shear heat created from the turning injection screw melts the thermoplastic binder, turning the feedstock to the consistency of toothpaste. A reciprocating screw then quickly forces the material through openings called sprue, runners, and gates into the custom mold of the component being fabricated. The typical mold is made of two sections with plane surfaces that meet to seal off the cavity. As shown here, the mold may consist of multiple cavities, enabling a number of parts to be produced in a single cycle. One section consists of a core, which fits into an impression or cavity in the other section, with clearances that produce the desired geometric shapes. All features are designed to permit the cavity to release the solidified form, which is pushed off the core with the ejector or knockout pins shown here. After filling, the mold remains sealed briefly to allow the feedstock to be cooled, freezing the mixture into the desired shape, its highly complex geometry fully formed. Generally, the total cycle time for injection molding a MIM part ranges from less than 10 seconds to approximately 60 seconds, depending upon the part size, complexity, and the number of mold cavities that are being filled. The ejected part, known as a green part, is still composed of the same proportion of metal and polymer binder that made up the feedstock, and is approximately 20% larger in all its dimensions than the finished part will be. The next step is to remove most of the binder, leaving behind only enough to serve as a backbone, holding the size and geometry of the part completely intact. This process, commonly referred to as debinding, may be performed chemically, catalytically, or thermally. After this debinding step, the part is referred to as a brown part. In the final step of the process, performed in the highly controlled atmosphere of either a continuous furnace or a batch furnace, the brown part is staged on a ceramic setter and is then subjected to a precisely monitored temperature profile that gradually increases to approximately 85% of the metal's melting temperature. The remaining binder is removed in the early part of this cycle, followed by the elimination of pores and the fusing of the metal particles as the part shrinks to its design dimensions and transforms into a solid metal part with a density of approximately 96% to 98%. The end result is a net shape or near net shape metal component with properties similar to those of one machined from bar stock. Of course, if necessary, post-sintering operations such as coining, machining, heat treating, coating, and others may be performed on the part to achieve tighter tolerances or enhanced properties. An almost limitless array of metal part geometries are possible with the MIM process. To truly benefit from all the possibilities metal injection molding offers, part designers should consult with a MIM parts fabricator right from the start of the design process. Parts that would usually be made by assembling multiple components can be designed as a single MIM part. Other parts can be made only through MIM. Complexity that would be cost prohibitive via multiple machining operations can be achieved cost-effectively through MIM processing. And medium to high annual production volumes can place MIM in the sweet spot of economic advantage over competing processes. The intimate knowledge of experienced fabricators about tooling considerations, proper material selection, and exacting design guidelines for MIM fabrication will ensure the success of your component. It is crucial to understand the tolerances that can be met by using the MIM process. By analyzing the dimensional MIM process capabilities, potential users can determine what dimensions they specify in order to assure part design integrity. In many cases, the MIM process can meet dimensional specifications of a part design that result in conformance to form, fit, and design. Knowing MIM process capabilities in early part development is essential to success. Every day, in some way, powder metallurgy touches your life. Look around you. No matter where you are, no matter what application you're considering, chances are PM components are already there, doing the job, achieving performance objectives, exceeding expectations. Wherever there's a tough job for a metal component to do, powder metallurgy is there. The preferred metal forming solution.